All right, we start. So we had talked about right. So there was some hand wavy thing I did in the last class. So x plus delta x is this, and then what was the linear equation without Hessian? Right, this one. So if you want, what do you actually want from this? If all these guys go to 0, you want value at f of x plus delta x to be lesser than fx, right? So basically, do all this. So maybe this guy comes this side, fx minus f of x plus delta x, then this guy goes that side, which is minus of xt transpose grad f. Now this thing should be negative and so on, right? So okay, let me do it. Huh? Vectorization of so we'll talk about that. Okay. So then you can come to this equation easily. Okay. So you want your delta x to be in a direction that takes you in towards the descent, right? That's what we were looking for. So if I just want to do this, what will it be? So what I want is f of x minus f of x plus delta x. What should this quantity be? So at this value, I mean the value here I want it to be lesser compared to at x. See, I want to take delta x in a direction where value decreases, right? And I want to take that direction where value decreases maximally, which is the direction of negative gradient. So this guy should be greater than or equal to 0. Okay. So if this guy should be greater than or equal to 0, what is this guy actually? Transpose grad f. This is negative. This is equal to this. All I have done is take this side, so fx minus this, take this side, so minus of this guy. So this guy should be greater than or equal to 0. In which case will it be so? So this dot product must be negative, right? And dot product gives you value between what to what? If you take dot product divided by the norm of the two vectors, you will get between -1 to 1, that is the cosine similarity. So how can you maximize this quantity now? By keeping delta x in a direction that is 180 degree of grad f. Okay? Is this fine? I mean, this is what we have talked about before, but I just made a hand wavy argument for this. Okay? Chalo. So now we continue with what we were doing. Any questions you have to ask? Why don't we use Hessian? Computationally expensive. In fact, it's so expensive that we just can't afford it. Okay? So no company in today's world can afford to build a Hessian for large language models today. No company can afford to do that. Okay, so what is batch gradient descent? What is, so tomorrow we'll come back to backpropagation, right? We'll do it much more in depth. I mean, we have already done in depth, but we need to continue. Yes. So there is one thing called batch gradient descent and stochastic What happened in this case? This is, so for one update, okay, how much do, so for one update, and I am basically writing here, for one update of what? Parameters. So in batch gradient descent, how many examples will you process first and then update? So training data set. So you go through the complete training data set, and what does this mean, go through the complete data set? What does it mean to go through the complete data set? Which function? Which function? Cost function? How do you apply cost function to each data set? Nee, how will you apply cost function? How will you get the value of loss for one particular example? So see, you have this neural network, whatever is there inside, you have input here, you have output here. We call output to be y hat always, right? It does not matter which one. Now, this is your function f that maps input to output. And for us, this is a neural network, okay? Now, this f, so this is your neural network. What is j? J is a different thing, that is function of y hat. And we know y hat is function of all the parameters in this function f here, neural network here. So you have input. Now what does it mean to say go through all the examples? Let's say you have m examples. So first example goes through this. You compute j for that example. Second example goes through this. You compute j for that example. Likewise, you pass all the m examples through this and you compute j for all of them. What do you do with all these j's that we have accumulated? You add all of them. You add all of them, what do you get? You get the final j. Okay? So you get that particular j. This means what part is completed in our 4 lines of gradient descent? Compute j part is now complete. Okay? So compute j is done. Now next. So what does it mean to say go through the complete data set? Your whole data set will pass through this neural network. For all these m values, for all these m examples, the values of parameter will be same or will it be different? It will be same for all these, right? Because that's what it means. We are saying use complete training data set to update. So you are not going to update before you have passed the whole training data set. So this particular function is fixed right now. It's a completely rigid fixed function. You pass every example through it, collect the loss for every example. add all of them, what you get is a cost function. So these terms are used interchangeably, loss, error function, cost function and so on. So you finally get the cost function, you compute j for this cost function. So j equal to summation over m ji, okay, I mean summation I equal to 1 to m ji. Now, so that was batch gradient descent. Second is stochastic gradient descent. What happens in this case? So for one update you need one example. What will happen in this case now? Right, so what happens in this, we will talk about the behavior of these three. So what happens in this case now? So what about this j? Which is robust j? This one or this one? This is, let's say, ji. For every example, which j is robust in whatever sense? Why do you think so? Okay, I'll pause this one for the time being. Now what happens in this case? So you have a batch. In this case batch size is 1, in this case batch size is m, right? So you have this whole spectrum, you can have from 1 to m. So this guy is somewhere in between, okay? Whatever that number is, let's say, let me fix it, let's say 32, right? But it can be 32, 64, usually you keep it power of 2. Why so? Because the number of cores in GPU will be most likely power of 2, okay? So you keep it like that. Done, let's say I choose 32. What will happen in this case? I will compute ji for 32 examples, right? So you compute ji for 32 examples. This is a middle path between these two. Now let me come back to our old space. So we have direction B. What was I using earlier? This was direction W. I've forgotten. This was B. How will my J equal to W square plus B square look like? So on this plane, if I want to draw contours, how will I draw them? Concentric circles, all will have center at 0, 0. So for all these circles, what is the property? Value of j is same, right? So if I take a plane that is perpendicular to this plane, cut this particular bowl shaped function, I will get a circle, right? They all will have the same j, same value. Now what was the good thing in case of these circle? When you take gradient, right? Gradients were perpendicular to these surfaces no matter where you go, because circle spheres, they have so many symmetries, they are perpendicular to wherever you go. Now if I start from here, if I do update for batch gradient descent, where will I most likely go? This side, okay. What happens in case of so now tell me, what is the difference between batch gradient descent, stochastic gradient descent and mini batch gradient descent? So in all these frameworks they call it stochastic gradient descent, but actually it is mini batch gradient descent. Yes, mathematicians, they don't study batch gradient descent or even stochastic gradient descent. We have mathematical bounds for stochastic gradient descent, where examples are replaced, because it will give you uniform probability. So one example will be chosen at uniformly at random from a set of m examples with replacement. What we do in CS is you simply shuffle and then start feeding the example. So what is studied is different from what is used in practice, but leave that. What will happen in case of stochastic gradient descent? I have one good J in case of batch gradient descent. Why one good J? Now what happens in case of stochastic gradient descent? I have a J for every example, right? Is it necessary that these two have to be the same? No. So for every example you are doing updates, right? Now in case of mini batch gradient descent, so if you go for stochastic gradient descent from the perspective of this new bigger J, the total J that we have, you might go something like this, But eventually what should happen? Eventually we expect it to converge to where this was converging, right? What about mini batch gradient descent? So what will happen in case of batch gradient descent if learning rate is chosen appropriately? Then basically you will come on this path. Whereas for stochastic gradient descent, because you don't really know, every example is having its own J. So with reference to this J, I can go in a very random zigzag direction. What happens in case of what was the other thing? Mini batch gradient descent. So it won't be as smooth as this, it won't be as random as this, somewhere in between, right? So whatever it is, but somewhere in between, not as bad as. Which ideal case?
Like if you are taking batch gradient descent, तो उसमें आपने देखा कि convergence एकदम smooth होगा.
When I say so, I am talking about a special function, this bowl shaped function, right? In reality, you can have a super bad concave function and you don't really know what will happen there. Yet, batch gradient descent is expected to be smoother. So on an average, I would expect batch gradient to be much smoother compared to mini batch compared to stochastic. But it really depends on the surface. Yes. How do you implement stochastic gradient descent? And देखो, these days in papers, what you see is, you don't see we run training for this many epochs. What do you see? What you see is something called training iterations. What is training iteration? So one iteration is counted as when you go and update the weight, right? So when you go and update the weight, that is your one training iteration. Now updates are very slow in case of batch gradient descent. What are the downsides of it and what are the positive sides of it?
Exact minima पे नहीं पहुंच पाएगा. Minimum minimum.
Exact minima पे in practice we will never reach, right? I mean exact minima is a point and you can't reach to a point that you decide to reach, right? In the end you will be reaching points, but it's very hard to reach to a point that you decide to reach. Yes?
We'll only get to know what mistake we have made.
Huh?
The mistake we'll only get to know about training it.
Right. So if you have a large, yeah, I think we have talked about this. So if you have a big training data set, it might take you days, right, to figure out that you have made some silly mistake. So what people wanted was, these things came because people wanted ki I should get to know about mistakes in my code as soon as I can. I want to start getting this behavior. So you can call it number of epochs now, you can call it number of training iterations. Whatever it is, you want it to decrease something like this. This thing you will see only in case of a batch gradient descent and only in case of a concave function like this when chosen a correct alpha. So this we would usually not see this if you are training some non-trivial neural network on a non-trivial training data set. What is likely to be seen is something like this, which will be expect that it will go and converge at some place. Okay. So in case of batch gradient descent, you are updating lesser compared to mini batch gradient descent, and even in mini batch gradient descent you are updating lesser compared to stochastic gradient descent. Okay. And these are just variations of gradient descent. Maybe you have, I don't know, maybe you have hundreds of variations of gradient descent. Okay. So if I ask you to write an algorithm for mini batch gradient descent, can you write? We know how to write it for batch gradient descent, those 4 lines. If I ask you to do it for stochastic gradient descent, can you write? How will you write that algorithm? And can you write it for mini batch? Right, you decide. Okay. Now next. So I think we are done with these things. Now let us try to make our cost function a bit more complicated. It will still stay convex, right? So we have talked about the best convex function that you can ever have. So convex functions are already good, and even in the set of convex functions we have chosen to be the, we have chosen the best convex function to discuss until now. Why best? Why is this best? Because search for minima lies on a line. Okay, wherever you are on the, so wherever you are, the gradient or the negative of gradient is always taking you to the minima. Okay. Now let us say if you have not like this, but something like, so not like this, but let us say something like, I am not able to make ellipses well, but they are concentric ellipses with 0, 0. If this is B, if this is W, can you help me figure out the whatever? Can you help me figure out how will things happen here? Help me write equation of ellipse first. Yes. So, see, if I have a large W, so or if I have a small b, I need a bigger coefficient to go to W here, right? So, how should this look like? How should my equation? Here see, J was W square plus B square, coefficient was 1 for both, nice concentric circles. We have ellipses, coefficient will not be same. So, J equal to W square plus B square, but these coefficients will be different. Give me some numbers. So, let us say so can I say something like this? Maybe this. What happens in this case? I am trying to take it very skewed. Okay. How does this function look like? Make sure that it looks like this, something like this. Yeah. This is what you are saying? So my A is 1 by 5 and my B is 1. Okay. Yes. How will you minimize this particular function now? First of all, I want to figure out where is the problem compared to these circles. Now so tell me which values have changed. So value of J has changed, fine, J is a function, there it was this, here it is this. What problem introduces? See, is this a convex function? It's a convex function with only one minima at 0, 0. And we have been saying that convex functions are good. So help me figure out how will I reach to minima using gradient descent for this particular function. Gradient descent, how does it work? Can you give me grad J? Grad J? So grad J will be, क्या कर रहे हो यार? Grad J will be 50 W 2B. What is wrong with this straight line? Right? So take any W, take anywhere, this one. What's wrong with this line? So my question is wrong. We want to descend in this direction, right? So let me change the color. Where I want to go is this one. This will take me straight away to minima. Okay. Now give me a gradient at this place, at any place W comma B. It is this one. How will this guy look like? Perpendicular to the surface, that is fine. So if you want to still have a look at, if you still want to visualize the cost function, how does it look like? There you had, you know, bowl shaped, kadai shaped thing. Here you have more of a boat shaped thing. Okay. Now what happens in this case? Help me visualize how will my gradient look like. How will my gradients look like? See, gradients will be perpendicular to, so are all these contours even for this function? For this function, for all these ellipses, will I have the same value of j? क्या कर रहे हो सोचो ढंग से. See how does the function look like? एक बार इधर. So how does the function look like? Earlier it was a nice bowl shaped function, right? So sphericals, spheres were there everywhere. This time you don't have spheres, you have compressed this bowl in one direction. If you still take a plane that is parallel to WB plane, it is going to cut this function at various points. And what will be the locus of such points? Ellipse, right? Because let's look at the other way around. You will have 25b square plus 25w square plus b square equal to 1, let's say. Then value of j is 1 for all those points that satisfy this equation, and that's equation of a ellipse. If you have 25w square plus b square equal to 4, then j equal to 4 for a family of points, and the locus of that is another ellipse. So all these things are actually contours. I have to flip them? How can j be?
Same, like if A, for example, if either axis, B is different. So how can the value of J be same at point E and this minor axis point E?
So what I am saying here is, at all these points, the value of j is same, and you say it cannot be. So why?
Because axis, the length of the axis.
So things were okay with this bowl shaped function. All you do is you compress this bowl in one direction, right? Okay, let me put it this way. It does not matter which cost function do you have. Will it have contours? Of course it will have contours, right? Because if you take a plane that is parallel to my WB plane, it is going to cut that particular function at various places. Sometimes contours will be well defined like this, and sometimes you can have contours like completely not defined, some random trajectory. Okay? So you will have contours for sure, we will take this offline. Okay? So your contours will be elliptical in this case. You have just moved from supersymmetry of circles or spheres to just one degradation, which is to ellipse. In general, you can still say ellipse is so circle is a special case of ellipse when these coefficients basically become equal to 1 or the same thing. Okay? You just give up this symmetry and you are already into problems. Give me the direction of grad j. So for example, at 1, 1, what is grad j? (50,2). So it has much more component in has much more component in W direction, so then I made a mistake. सही करो बताओ ये 25 किधर आएगा? No. See, slopes are gone. As you move away from 1D, slopes are gone. Because this is a 3D thing. So when a slope will be a plane kind of thing. So what you are looking for is a direction on this plane. So guys, एक बात बताओ, which is the direction of maximal increase? Again perpendicular to this. Okay, that is what this gives you, but my problem is, no, there is no problem, everything is fine. At 1, 1, is that sure? So because this should be W, this should be B, right? That's what I was asking for. So this should be drawing का, हाँ? इक्वेशन तो सही है. Fine. So now if you see, grad J has higher coefficient in direction W compared to B, right? For any point. Can you give me some points on this particular ellipse where line search will take me to minima? There are exactly 4 points. These guys, right, towards the major axis and minor axis. If I start from here, then negative gradient will actually take me to 0, 0. But what is the probability that when randomly initialized, you will start from any of these 4 points? 0. Okay. So the probability of starting from these points is 0. Now, your gradient looks like this. How many of you agree here? The gradient is, and how many of you are able to visualize this? How does this surface look like? See, we are into WB plane. We have some boat shaped curve here. If I move perpendicular to where I am, perpendicular to this concentric ellipse, then I will go into the direction of maximal increase. Let's say I don't go into this direction, I go perpendicular to this direction. What happens? If I don't go in the direction of gradients, I go into the direction of perpendicular to gradients, a very small step. Where will I go? कितने लोगों ने सोचा था कि डीप लर्निंग ऐसी होगी? So tell me again, if I don't move in the direction of grad J, I move in a direction that is perpendicular to grad J. Very small step, infinitesimally small. Where will I go? Perpendicular to this will take me downwards. I will move on concentric circles, right? So value of J will not change. I want you to visualize this, so I won't go forward if you don't. this is my 0 comma 0, this is my 0 comma 0, this direction is B, this direction is W. Okay, can you visualize how does this surface look like? It looks like it's a symmetric thing, right? If I look it this way, it's symmetric, backward it is symmetric, this way it is symmetric, this way also it is symmetric. The only difference is that this symmetry, this direction symmetry is different from this direction symmetry. In case of circles, all 360 degrees are the same. I can simply rotate a circle and it won't matter. If I rotate this particular bowl, what will happen? I will need to change my axis, right? In case of a circle, I don't need to do any damn thing. Okay, now, so I'm not rotating this. Now this particular surface, if I want to go in the direction of maximal increase, I am here right now, where should I go? I am at 0 comma 0. I can only move in my plane W comma B. So I need to, so let's say if this is concentric circle, यार ये कैसे समझाऊं भाई, मेरे को तो trivial लग रहा है. Some of you are there, but I want everyone to be there. How many of you want to be there? Okay, let's put it this way. All right, then we work hard. Huh? So everybody visualize this it for circles. So then boat में क्या दिक्कत है यार? See, you don't have concentric circles anymore. Okay? अच्छा एक बात बताओ. Okay, forget everything. What will be the direction of steepest increase according to you? I want to make another circle. I want to make another ellipse. What will be the direction of steepest increase? अच्छा एक बात बताओ. If I go in this direction, will it be the steepest increase? Why not? If I walk this much, let's say I reach here. Okay? If I reach here, I will have some value of j. If I reach here, I will have some value of j. Now I make a ellipse for that. Where is this ellipse? So I have to move this much. Can you give me another direction where I will move minimally and still give the same value? This one, right? And this happens to be the direction of gradients, which will increase my j maximally. If I move in that direction, my increase in j will be maximum. Everywhere else it is going to be less than that. Okay? If I move in a direction that is perpendicular to this guy, I am descending in a maximum fashion. Okay? Questions here? Is that fine? Okay. So now tell me, this is my thing. Is it passing through 0 comma 0? In case of circles, no matter where I am, right, my negative of gradient is always taking me to minimum. What will happen in this case now? I want to go to red line, but I have no idea how to follow the red line, because the equation that I am following, it is taking me in this direction. What do I do? So let's say I start from here. Let's say I start from here. If I start from here, what will happen? This is my grad j. So my negative of grad j will be this one. So let's say I go in this direction and come here. What will make me bring here? Probably my alpha was high. But you think of so we already, so just a second bhai. हाँ. See, ellipses are everywhere. you cannot go to a point which is not on a concentric ellipse, right? No matter where you go, you have some value of j there, and there exists a ellipse for which the same j exists, because it's a continuous function. Okay, just a second, देखो. चलो छोड़ो, 950 is already done. So there are these function, you can draw this function. I was not able to draw this well. There are online places where you just write this function and it will give you a very skewed function. I mean 25w square plus is not this ellipse, it's a very thin ellipse. आज 3 तारीख है ना. Yes, next. So Astha, Adhiraj, Akshat. Oh. Amit, Arohi, Arukshita, Ashmit, Disha, Divyanshu, Ishan, Garv, Himanshu, Kanishk, Kashish, Keshav, Kushagra, Melissa, Mihir, Muskan, Nilesh, Niharika, Paras, Payal, Ridhika, Riya Singh, Saurabh Saini, Srishti, Shreyansh, Siddhi, Saurabh Yadav, Swastik, Vaibhav, Vrinda, Yash Puri, Abhinav, Archita and Nitin.